Swayam Prabha. Digital India. Educated India.
Welcome to Module 53 of Point-Set-Topology course, Part 1. Today we will continue the study of normal spaces, characterization of normal spaces. Last time we did characterization due to Horizon. Now we will do the characterization due to Tietze. Tietze's characterization is another landmark, but it actually uses the Horizon's characterization, construction of continuous functions. But it is quite mysterious in a sense that here we have only one closest set. So it requires quite a ingenious mind to have explored this one. So it is not at all easy to come up with this kind of idea. So let us look at the statement here. A topological space X is normal if and only if it satisfies the following condition, which I have put as Tietze condition. So what is the condition? Given any closed subset E of X and a continuous function G from E to -1 plus 1, there exists a continuous function F from X to -1 plus 1 such that F restricted to E is G. Okay. Obviously, here E is a non-empty closed subset. Okay, that is, otherwise we don't have any continuous function G from E to -1 plus 1. So this is the hypothesis, given a closed subset and a continuous function. Okay. So there is no need to worry about that E being closed, E being empty and so on. So every continuous function defined on a closed set can be extended to a continuous function, retaining the codomain as it is, namely any closed interval. So model we are using -1 to +1. I have already told you that you can always change the codomain to any closed interval each time. Okay, so that is not very crucial. But now instead of 0, 1 as in the previous theorem, we will use -1 plus 1, which is more convenient for the writing down the proof. Okay. Assume that X satisfies the TC. Given any two disjoint closed subsets A and B, subset E, put E equal to A union B and apply this condition to get a function G from -1 to +1, namely G of X equal to -1 and G of on X belong to A and G of X equal to +1 on X1 B. Okay. G is continuous because A and B are disjoint closed sets. Okay, so this makes sense. Only two values you have taken. On A it is -1, on B it is +1. But now G will extend to a whole function from x to minus 1 plus 1. So there is an f here, that f restricted to E is G. Okay. So that is the condition for the Urysohn's characterization, UC. Therefore, X is normal by the above theorem. All right. So we have taken a shortcut here, used Urysohn's characterization instead of trying to prove open subsets, etc. All right. But in the converse proof also, we are going to use Urysohn's theorem. So one way is done. Now let us prove the converse. Again, the converse is taking up some time. Assume X is normal and E contains X is closed and map G is given. Okay. G is defined only on E and it's continuous there. We have to construct a map F from X to minus 1 plus 1 such that F restricted to E is G. So here we shall use the fact that set of all continuous functions from X to minus 1 plus 1, okay, they form a Banach algebra, Banach space, remember that, with the supremum norm. Remember that we had introduced the set of all X to R or C or whatever, and then we took the bounded functions there on which we put the supremum norm. Now, if we have continuous functions on X, okay, they may not be bounded, but here I am taking they are bounded by actually minus 1 plus 1. The values are inside minus 1 plus 1. So this will be a subspace of that Banach algebra. All right. This norm makes sense because now all functions are taking values from minus 1 plus 1. Okay. We also saw that the continuous functions, okay, form a closed subspace of this Banach algebra, and therefore this itself as a non-linear space, it is a Banach algebra. That means Cauchy sequences will converge inside this one, which just means that if you take a Cauchy sequence of continuous functions from X to minus 1 plus 1, you can take the limit in the larger space, but that limit is continuous. Therefore, it is in the smaller space. Okay. So this also you have seen the convergence with respect to the supremum norm is nothing but automatically it's uniform convergence. Okay. So this is what we are going to use. Essentially, if you don't want to use all these terminologies, all that just means that if you have a sequence of continuous real-valued functions, okay, which converges uniformly, sequence of continuous uniformly to a function, that function is continuous. So this is the fact that comes out of ordinary analysis, so which we are going to use it now here. Okay, how do we are going to use? Inductively, we shall construct a sequence Fn from X to minus 1 plus 1 such that summation Fi's, these are partial sums. That's a sequence. Not Fn. The partial sum, that sequence converges uniformly to a function f from X to minus 1 plus 1. And it has this property that norm of G minus I raised to 1 to Fi converges to 0. This norm, because G is only defined on E, should be taken on E. So same norm restricted to E, okay? So all these Fi's restricted to E. Of course, Fi's make sense on the whole of X, but G makes only on E. So you have to take C of EX. Okay. So that is the meaning of this one. So this is what we want to do now. So I will explain these things and more carefully in what comes here. Put Rn equal to 2 power n minus 1 divided by 3 power n. Take G naught equal to G. Having defined the map Gn from E to R for some n, inductively we are going to construct the next Gn plus 1. So for that, put An equal to Gn inverse of minus 1 to R minus Rn, and Bn equal to Gn inverse of Rn to 1. Then clearly An and Bn are disjoint closed subsets of E, okay, which itself is closed in X. Therefore, An and Bn are disjoint closed subsets of X. Hence, by Eugen's lemma, we get a continuous function chi An Bn from X to minus 1 plus 1. Remember, this chi N Bn is a continuous function which has the property that on An it is equal to minus 1 and on Bn equal to plus 1. That is all we are going to use it here. Okay. After that, we put Fn equal to Rn times chi of An Bn. Finally, we define Gn plus 1 as Gn minus Fn restricted to E. Gn is defined on E already. Fn is defined on the whole of X, but we take Fn restricted to E and take Gn plus 1 to be Gn minus Fn restricted to E on the substrate E. The inductive definition of the sequence Fn and Gn is over. Next task is to show that these things converge to whatever we wanted to. Namely, first of all, Gn and Fn are both continuous. Norm of Gn is equal to Rn times norm of chi n An Bn, that is 1. Therefore, it is Rn. And since summation Rn 1 to infinity is actually 1, so it dominates this norm of Rn. It just means that I ring to 1 to n Fi converges uniformly to the function, so function continuous function automatically because uniform conversion, and it takes value between minus 1 and plus 1. Okay, so this function f is now continuous because it is continuous. It is a uniform limit of finitely many fi's here, and then n tends to infinity. So these fi's finitely many f's they are continuous. N tends to infinity, uniform convergence. Therefore, f is uniformly f is continuous. We now claim that the second part, namely norm of Gn on E, that is supremum of all Gnx modulus Gnx, where X ranges over E, right? That is the definition. We want to say that this is less than or equal to twice Rn minus 1. Again, the proof will be by induction. When n equal to 0, R minus 1 is nothing but 1 by 2. Okay, and twice Rn is 1, and G naught is our function G, which is taking value between minus 1 plus 1. Therefore, norm of G naught on E is less than or equal to 1. Okay, so assume that this statement is true for some n. Then we shall prove it for n plus 1. Okay, so let us examine what happens to the function Gn plus 1. Suppose X is inside An. By the very definition of An, Gn of X will be between minus 1 to minus Rn. So it is less than or equal to minus Rn. On the other hand, the induction hypothesis says that minus twice Rn minus 1 twice Rn minus 1 is less than or equal to Gnx. The modulus of this one is less than or equal to twice Rn minus 1. This is the definition, this is the induction hypothesis. So if you put them together, now you subtract Fn, subtracting Fn is now on An, it is minus Rn, right? So adding Rn. So what I get is minus 2 Rn, which you can verify is same thing as minus 2 Rn minus 1 plus Rn, that is less than or equal to, this is Gn of x plus Rn, but this is the same thing as Gn plus 1 of x now, because plus Rn is same thing as minus of Fn. Okay, so Gn is less than or equal to minus Rn here, Rn plus Rn is less than or equal to 0, and 0 is definitely less than twice Rn plus 1. Okay, exactly similar reason, not exactly same reason. When you take x equal to x is inside Bn, this becomes now minus Fn becomes minus Rn, and we will have left and right hand etc. We have to correctly choose. Finally, you will get a similar thing, namely what you get is that minus 2 Rn is less than or equal to Gn plus 1 of x less than or equal to plus 2 Rn. So what remains now? Look at a point which is neither in An or in Bn. Okay, take a point which is nor in An nor in Bn. Okay, then both An and Gn are in the interval minus Rn to Rn by definition, because if it is not in An, it is bigger than minus Rn, not in Bn, it is less than Rn, less than or equal to Rn. Okay, so such a point automatically satisfies Gn plus 1 of x, okay, less than or equal to Rn plus Rn, and bigger than or equal to minus Rn plus minus Rn. So modulus is less than or equal to twice Rn, because both Fn and Gn are inside this one. Fn is always just minus Rn times 1 minus 1 to plus 1, Rn times minus 1 to plus 1. Okay, so this completes the proof of inductive claim that namely Gn of V is less than or equal to twice Rn minus 1. For the same reason, because summation Rn is convergent, this is dominated by this twice these things, it will follow that Gn of x converges to 0 as n tends to infinity, because these things converge to 0. Okay. Now, what is this G, that mysterious thing? Why G and Gn? That's clear, because Gn is nothing but remainder after n terms. Okay, I couldn't say that one because before that I have to show that the series is convergent. So we have shown that Gn converges uniformly to 0 inside E. But now if x is belong to E, then Gn plus 1 is Gnx minus Fn of x by definition. What is Gnx? Gn minus 1x minus Fn minus 1 of x. So you club them together, it will become Gn minus 1x minus Fn minus 1 plus Fn of x. But again you apply it to Gn minus 1, it will be Gn minus 2 minus Fn minus 2 of x plus all these. So go on doing that till you hit G naught. G naught is Gx, and this term will become summation I into 1 to n Fn. First Fn, Fn minus 1, etc. up to F1, all these terms will come. So Gn plus 1 is nothing but Gx minus I into 1 to n Fi of x. This is the second term there in the condition. We wanted to show that norm of this converges to 0. Norm of this same thing as Gn plus 1 of norm of this one. And we have shown that this converges to 0. Okay. So you see, this is nothing but inside E, this is just the partial sum, okay, and this is remaining after n term. That is the whole idea. Upon taking the limit, this is 0, this will be become f now, because ident 1 to infinity is our f, all right? So gx minus fx norm is 0, which just means that gx equal to fx. So this all happening for every x inside T. So that completes the proof of Tietze's theorem. So let me make a few comments here. Yeah. Since any two closed intervals, I am making this comment again, of positive length are homeomorphic, okay, we can use, instead of -1 + 1 or 0, 1, we can use any interval AB, okay. But in the proof of the above theorem, it was crucial that the codomain was a closed interval. You are going to take limits of certain, for each point you are taking limits, so they are just values. So the limit point could be in the endpoints. I mean, that is possible, right? So even if you start with the function, suppose the function given g is taking values in the open interval, extended function may not be taking values inside the open interval. It may hit A or B. That is possible, okay? Yes or no? So, because if you take open intervals, open interval is not complete, so you can't use all these completion results. That is the whole idea, okay? But you look at the statement of the Tietze theorem, that will not suffer. In other words, I want to have a theorem. Suppose G is a function from a closed interval to an open interval. Then I can extend it from X to open interval itself. So that is the statement, okay? That's not the part of the statement, but it's extra statement. We have to work out, and there is a trick which will help us to prove such a theorem. So let us do that. So this is the statement here. So I have stated a separate theorem. Let X be a normal space, E contains X closed. Then given any continuous function G from E to open interval -1 + 1, there exists a continuous function F from X to open interval -1 + 1, such that F restricted to E is G. Okay. Directly from the theorem that we have proved, this one does not follow. That's what I made a remark. Okay, what follows? You can think of this as closed interval, by taking inclusion of this one in closed interval. Then you will get a extension also with closed interval, right? So that much is true. Now, how to come back to the open interval? Here is a trick. Applying Tietze extension theorem 4.39 to the map G treated as a function from E to -1 + 1. We obtain a continuous function F1, let us call it F1 because this is not going to F, from X to -1 + 1 such that restricted to E it is G. What may happen is, look at F1 inverse of -1 and +1, just the 2 points. Put that as A. That is a closed subset. This may be empty If A is empty, then we are happy. That means X is inside open interval minus 1 plus 1. If A is not empty, then we have to work harder. Okay, in any case, A is a closed subset of X, disjoint from E. Why? Because to begin with, we have started with a G such that G is taking values strictly inside minus 1 plus 1. And F restricted to E is G. So this A and E are disjoint subsets and both of them are closed. Hence, you can apply Erythmo's lemma here, okay, to get another function h from x to 0, 1 such that h of A is 0 and h of E is 1. So you see, here I am using again 0, 1 instead of minus 1 plus 1. So that is it's deliberate. It is not just arbitrary. Okay. So h of A is 0 and h of E is 1. So whole idea is you don't want to disturb the E part. So you have put it as 1 here. You don't want this A part. So you have killed it. H of A is 0. That is the whole idea. Now you multiply the original F1 with Hx. Take Fx equal to Hx into F1 of x. Okay. This is a product of two functions, both of them taking values in minus 1 plus 1. Minus 1 plus 1 and other one 0, 1 anyway. So this will take values in minus 1 plus 1. There is no problem and it's continuous. And when you put x equal to x inside E, this Hx is 1. So it is F1 of x, which is G, the original G. Therefore, that is also over. All that you have to show is that the new function f takes values inside minus 1 plus 1 open. Right? Then the theorem is over. Okay, why it doesn't take the value minus 1 and plus 1? That's what I have to show. All right. So suppose modulus of fx is equal to 1. But what is modulus of fx? What is fx? Fx is hx into f1 of x. Okay. Suppose for some x it is equal to 1. Either it is minus 1 or plus 1. Then f1 of x is less than or equal to 1 modulus and hx is inside 0, 1 for all x. Remember that. We must have modulus of fx is actually equal to 1. Even if any one of them is smaller than 1, the product will not be equal to, modulus will not be equal to 1. Okay. So both the modulus must be equal to 1. Hx modulus doesn't make sense because this is already positive, non-negative. So it's actually equal to x. If hx is 1, after multiplying by hx, what do you get? F1 of x is equal to fx, modulus of x is equal to. But modulus of x, f1 of x is equal to 1 implies x is inside A. Remember that A was defined as f1 inverse of minus 1 as well as plus 1. But then h is 0. H of A is 0. But just now we have h of A is 0, but the right hand side will be 0. This can't be 1. So we have shown that h is also 1. So that contradiction proves that modulus of fx is never equal to 1. Okay. So I have said that this is a trick. This kind of tricks are used quite often in algebraic topology also. So in summary, what we have proved is Tietze extension theorem, the codomain can be replaced by any bounded open interval instead of a closed interval. But R is homeomorphic to any open interval, therefore you can take the whole of R also. finally, if you carefully watch the proof of the above theorem, you will notice that it can be easily adapted to half open intervals also. If you don't want both of them, you have to work only for one of them. That A which you have taken f inverse of minus 1 plus 1, you take A into only one of them. Okay, inverse of one of them. So it will work for half open intervals also. Okay. Therefore, all these statements can be collectively called as Tietze extension theorem for normal spaces. Given continuous function on a closed set, taking values in open AB, open R, closed AB, closed A, open B, whatever you take the codomain, okay, in the same codomain, there is a continuous extension of the function g to a function f on the whole of x. So that is the way you have to understand Tietze extension theorem at various places. Whichever form is necessary for you, you can use that. All right? Urysohn's characterization of normal space drew a lot of attention. Tikhonov came up with an idea of adopting a somewhat weaker version of the Urysohn's characterization, but one is stronger than regularity. So another concept came in between, what is called as complete regularity. A space X is called completely regular if it satisfies the following condition. Given a closed subset f of x and a point x belonging to x minus f, remember this was the hypothesis for a regularity. Instead of two disjoint closed subsets, one closed subset and a point outside it. Okay. So then instead of open sets and so on, now you have a function now. There exists a continuous function f from x to 0, 1 such that f of x is 0 and f of capital F is 1. So this is a perfect mixture of regularity condition and Urysohn's criteria. A mixture. Such a thing is called complete regular space. As usual, normality does not imply CR simply because singletons may not be closed. This complete regularity is an important concept in metrizability problems. Even the Urysohn's lemma, I think Urysohn had finally to try to prove some embeddability results through which he wanted to prove metrization. That is why he explored this one. He came up with this what is so-called Urysohn's lemma now. Okay, so this complete regularity is important in metrizability problem that will be discussed and taken up in part 2. So I'm just giving you a glimpse of that. Even if you forget it, it's okay. So I think you are now convinced that why Urysohn's lemma is so important. All right. So let us meet next time. Thank you.